I want to start section 4.7. These are differential equations called Cauchy-Euler equations. Cauchy is a mathematician, French mathematician from the early 1800s. His name is all over lots of areas of math, but in particular a lot of complex analysis. Euler is probably the most proficient mathematician that's ever been, Swiss mathematician from the 1700s. His name is just everywhere. So he's done so many things that there's actually things that he's done that are named after like the second person to do them because he's just done so much. Anyway, so Cauchy-Euler equations are equations where we're still talking about second order differential equations, but they're going to be equations like this. You're going to have some constant. Let's just call it a. You're going to have a x squared y double prime plus b x y prime plus c y equals f of x. So Cauchy-Euler equations are exactly the ones where the derivative that you're taking, so if you're taking the second derivative, you have an x to the second power in front, and if you're taking the first derivative, you have an x to the first power in front, and so on. So those are called Cauchy-Euler equations. And it turns out that what you can do in the general shape of these equations is going to be something like y equals x to the m. So just like when we were talking about equations with constant coefficients and we looked at e to the rx, here we're going to look at y equals x to the m. And the reason why that's going to be a good idea is that if you think about x to the m, when you take the derivative, you're going to get a constant times x to the m minus 1. But if you're multiplying by x, that's going to make this an x to the m. And this is an x to the m. And likewise, this will be x to the m minus 2 times some constant. So when you multiply by x squared, you again get an x to the m. So all of those terms are going to be very nice for us. This is going to be the general shape of our solution, y equals x to the m. And then once we have linearly independent solutions, we know that it's a second order ODE, so we'll have two linearly independent solutions. We can go from there. So what we're going to do is we're going to start with the homogeneous Cauchy-Euler equations. So let's just go through and let's do some examples. I don't want to do too much theory here. I just want to kind of jump in, see what happens, and see how this works. But let's look at solving. So let's try and solve the differential equation x squared y double prime minus 4xy prime equals 0. This is one that actually you could solve pretty easily. You could solve this pretty easily without this method. You could do substitution. This is a pretty straightforward equation. But anyways, you could substitute. It turns into a first order linear problem, so you could find the multiplicative function, the multiplying factor. But anyways, let's do it as a Cauchy-Euler equation. So what we're going to do is we're going to let y be x to the m. And then what we're going to do is we're going to look at, let's see, y prime. So y prime is going to be m x to the m minus 1. And y double prime is going to be m times m minus 1 x to the m minus 2. So if we substitute those back in, what we're going to do is we're going to get, let's see, x squared times m minus 1 times x to the m minus 2 minus 4x times m times x to the m minus 1. So that's minus 4x y prime equals 0. And again, the x to the m terms, let's factor those out, and we're going to be left with m times m minus 1 minus 4m. That's all times x to the m, and that's going to be equal to 0. And again, what we want to do is we want to figure out what's the value of m so that the left side is always 0 no matter what x is. So in other words, we need to think about when's that coefficient going to be equal to 0. So we're going to have m squared minus m minus 4m will be minus 5m. And that'll be 0 when m is 0 or 5. And so that means that we're going to have two solutions, x to the 0, or just a constant, and x to the 5th. And those will both be solutions. So that means that our general solution is going to be c1 times x to the 0 plus c2 times x to the 5. Or if you prefer, which I do, x to the 0 is just 1. So it's just c1 plus c2 x to the 5. Okay, so those are Cauchy-Euler equations.